Hey everyone, let's start. This is XCamp USACO solution discussion for the server. We just have the test this weekend. So today we are here to discuss the solutions. This is Charlie. I'm the co-founder and the CEO and the principal of XCamp. I also still working in Google. We'll have an introduction on XCamp first. Then we will have the tutorial on the server contest. Also, we will introduce the XCamp classes and how to prepare next USACO. Finally, we have the QA sessions. XCamp was founded by me and my Google colleague Yuan 5 years ago. We provide classes from beginner to the master level. I mean, even the ROI contest level. We have curriculums developed by senior coaches from ROI to NOI, all these high-level medalists. Also, we have supported by senior engineers in high-tech companies. We have built solid knowledge foundation for our students. We have 4 USACO camp students in the last season. Also, we have very good USACO passing results across all levels. Generally to say, we provide very serious coding education to the beginners. We help the students to love coding. We provide algorithm and data structure foundations to help students to have a complete knowledge on the algorithm and data structure. If going in advance, the students will go to competitions. Some of them might not. You can also have very strong coding and engineering background, so you can go to academia or go to industry. So most of you, after you learn this, have a solid foundation, you might choose a career for you. But still, if you don't, you can have a strong foundation for even other careers. Okay, let me turn the session to our teacher, Max, here. Let me stop sharing. Max, are you there?
Yeah.
Okay, great. Let me make you the co-host. You can share your screen.
All right.
Max, would you give us a quick introduction about your background?
Yeah, sure. So, hi everyone. I'm Max. I'm one of the instructors for XCamp's USACO Grandmaster classes. So I've previously worked with 602 and 603. I'm currently in charge of teaching 602. So that's the class that prepares for passing gold and into platinum. I guess my own competitive experience is I've done USACO in the past up to the Platinum Division, and in college I've done ICPC, which is the International Collegiate Programming Competition. So I qualified to the World Finals last year and got a bronze medal at the North American Championship. So I've done this for a while now, and I guess now part of my efforts is focusing a bit on teaching, and I guess today I'll be talking about the silver problems and presenting some solutions and intuition for how to solve them. Yeah, let's start with the first problem. So I have the statement over here, but I'll briefly summarize it here. So essentially, we have a setup of like n barns, and they're connected in a graph with n-1 edges. So essentially, they're in a structure of a tree. So a tree graph, so n nodes, n-1 edges, and node cycles, that type of deal. So I'll draw an example tree here. So the sample input, for example, is we have a tree with barn 1 is connected to 2, and 2 is connected to 3 and 4. So let me actually move this over here. Yeah. And so this is an example of a tree here. And we also have these H hay bales, HI. So essentially the ith node has HI hay bales on it. So for example, the sample input gives us that initially there are 2 hay bales at the first node, 1 at the second, and 4 and 5 here. And so our goal, so what is the goal here, or what are we trying to do? So we have these, essentially in one operation, we can choose two adjacent nodes, and we can move any amount of hay bales from one to the other. So for example, in one move, I could take like 2 hay bales here and move them both to over here. So I basically remove 2 hay bales here and I add 2 hay bales here, so that after this move, I would have 0 hay bales on this node and 3 hay bales on this node. And then maybe in a second move, in a second operation, I can move some more hay bales from here to there, and so on and so forth. And so why am I making these moves? Well, the purpose of making these moves is I want to construct a sequence of moves with we want to use the minimum number of moves. So we can't just use any amount. We want to minimize. And we want to make the number of hay bales on all equal. So make all equal. We want to ensure the same number of hay bales on every single node. Yeah. So I guess, yeah. So, all right, how can we approach this problem? So anytime you see a problem about like, doing some sort of like operation on tree, something adjacent, it's a little difficult to just kind of like jump at it and like immediately consider like doing operations with some random node in the center or something. But it's much easier to consider from the perspective of leaves. So leaves are these nodes on the ends with a degree at most 1. They are only connected to at most one other node. So let's consider this node, for example. So first off, if we want to make all the nodes have equal amount of hay bales, then at the end, each node should have the sum of all the hay bales divided by n, right? Because we're distributing them evenly. And so in this case, it would be in this case we would want let's see, 2, 1, 4, 5 over 4. So this is working with 12 over 4. So we want 3 hay bales. We want 3 hay bales on each vertex. Yeah. So now let's look at this is the desired amount of hay bales on each vertex, each node. So now let's look at this leaf node here. So this leaf node currently has 2 hay bales, right? So we want 1 more hay bale on this node. And this is unavoidable, right? No matter what solution we construct, at some point, we're going to have to move an extra hay bale over to this node. There's just no way around that. So we're guaranteed like this leaf is going to cost us this leaf node is going to cost us at least 1 move, right? At some point, we have to move a hay bale from this node over here to this node over here. And so I guess let's just make a note of that. So what I'm going to say is I'm going to make a note. I'm going to say, okay, from here, I need to move 1 hay bale over here. Now, I'm not going to worry about whether it's possible or not. Maybe it's even not even possible at the moment because there might not be enough hay bales at the adjacent node, but let's not worry about that for now. What are some other leaf nodes in this graph? This is also a leaf node, right? This only has degree 1. And what is this one has 4 hay bales initially. So we need to remove 1 hay bale from this node. And again, this is required. There's no way around this. At some point in this process, we're going to have to take an extra hay bale from this node and move it somewhere else. So this is also guaranteeing us another move. So we can also make a note here that this node is going to move a hay bale to the adjacent node. It's going to move 1 hay bale. This is going to happen at some point. I haven't talked about when yet. I haven't decided when, but it will happen at some point. And then finally, we have this node, same logic, right? This node has 5, but we need to subtract 2 from it. So at some point, this will move 2 to this node. And in this case, it actually happens to work out because we can do this in 3 moves. We can move 1 hay bale from here to there, 2 hay bales from here to there, and then 1 hay bale from here to there, and that would work out. So perhaps we should look at a more complicated example where you can't just like make it work out like that. Just do the operations in any order. So here's another example that's going to be a little more complicated. Here, let's do this. Okay. And let's say the initial weights are 7, 8, 2, 3, 5, 1. And what does the last one have to be for it to be possible? Let's see, 11, 18, 26. and 7 nodes total. So I need 2 more. Yeah. Okay. So in this example, okay, well, let's try the leaf strategy again, because well, that worked pretty well last time. So let's look at this leaf node, for example, the one with 1 hay bale initially. So our target should be, the sum of these is 28 over 7, so we have 4. That's the target. Yes. So we want 4 hay bales on each node. So this one's going to be demanding 3 more from the node that is adjacent to. Similarly, this node is going to demand at least 2 more, and this node is going to demand at least 1 more. Here, but the issue here is that this node only had 5 to start, right? That's kind of an issue. We can't really just we can't take a total of 6 more hay bales from this node because it doesn't have enough. So here's how we're going to go about it. Essentially, what we're going to do is we're going to, after we process each leaf node, recurse delete them, and that's going to lead to more leaf nodes. So we're going to delete these nodes after we process their effect, and we're going to have a net of this, and we're basically going to subtract, or basically going to say that this node needs 6 more, or needs 6 extra. It needs 6 extra so that it can give it to each of its leaves that were just deleted. So actually, maybe I shouldn't explicitly erase them. I'll just scribble them out so you can still see them for reference. So what I'm going to do is, just going to go ahead and just delete them like that. And so this one is going to, this one is going to require, this one needs 6 more. And this is kind of an intuitive thought, right? Because you think okay, once I have processed all the leaves, I can delete the leaves, and then that will create new leaves, right? Because when I pluck off some leaves from the tree, the ones that I used to be attached to, those become new leaves, and so on and so forth. So now this node 5 is a leaf, except the target for this node is not just 4. This node doesn't just require 4; it requires 10, right? It requires the initial 4 for itself plus an extra 6 to give to its now deleted leaves. So from this node, I'm going to be demanding 10. It already has 5, and so it's going to need 5 more from its adjacent neighbor, right? So that's so again, I'm going to make an indication that we need 5 more from its adjacent node, and then delete it. So now here, this one is okay, this one needs 5 more, right? So this one needs a total of the initial 4 that I needed, plus the 5 extra that it's going to give to its adjacent vertex. So it needs a total of 9. It already has 2, so it needs 7 more. So actually, we can't talk about this node yet because this node has 2 adjacent edges, right? So it's not a leaf node. And because it's not a leaf node, this is why we were talking about leaf nodes before. If it's not a leaf node, it's unclear who we should try to call from. Should we try to call from this node or some combination? It's unclear. So we're not going to worry about this node for now. Instead, let's talk about this node because this node's actually a leaf. So this has 8. It only needs 4, so it's going to give an extra 4 here. And similarly, this one's 7, right? But it only needs 4, so it's going to give an extra 3 over here. And so now, the total number of nodes on this is the total number of hay bales on this node is going to be 3 plus 2 plus 4, which is 9. It saves 4 for itself, and it has remaining 5 more to give to its adjacent vertex, which is precisely what we want. So let's take a step back here now. So what I've done here is you can see here that I've basically drawn these arrows, right? I've drawn arrows saying that this node is going to give this much to the other node. So it's this node gives this node 4, this node gives this node 5, this node gives this node 2, and so on. Now, I need to actually reconstruct the answer, right? So to actually reconstruct the answer, I need to basically pick an ordering for how I'm going to do each of these transfers, right? I can't just do them in a random order because if I do them in a random order, I might accidentally try to do these ones first, and then I'm stuck because this node doesn't have enough hay bales. So I got to do them in a good order. And There are a number of ways of approaching this problem, finding a right order for it, with varying levels of complexity. And I will describe one way that ends up being quite simple to code. Yeah, so before we move on, before we move on, I should also talk about whether or not this is the minimum number of moves, right? Because this is just a sequence of n-1 moves, but is it the minimum amount? And well, this is in this case, it's kind of required, right? Like each leaf requires either like more or less, and so it's kind of like there's not really much choice to be made here. So like each of these arrows is kind of forced by some leaf that we were considering at some point. So this is optimal. And to show that the answer is not always n-1, sometimes a leaf will have exactly the right amount. Like for example, it might be like 3, 3, and a simple example like this, 3, 3, 3. This node already has the desired amount, so it would require 0 from its adjacent node, and 0 is not an operation, so we just don't perform it. But in this case, each of the arrows actually do have non-zero values on them, so they are a necessary move. All right, so let's talk about reconstructing this sequence now. I guess before I reconstruct the sequence, let me make sure no one has any questions on anything so far. So yeah, I guess this all makes sense to everyone. Yeah. Yeah, so actually, so some people have astutely pointed out in the chat that yes, this is a DAG, a directed acyclic graph. Like this is an edge from this to this. This is an edge from here to there, and so on. And so you could do a topological sort to recover an ordering for performing these operations. So you start with a vertex. A topological sort is just an ordering of the vertices, an order, so that you only point from earlier nodes to later nodes. So you never have like a conflict. And this obviously works because, any node that doesn't have anything pointing into it means that it doesn't require any more hay bales, so it's not going to receive any more hay bales. So it already has the maximum amount that it's ever going to have throughout the entire process. So it's always going to have enough to give to its outgoing edges. So that's why a topological sort would work for this. Topological sort is technically a goal topic, but there is another way of, I guess also I'll present another way of doing this as well. So first off, let's say we root the tree arbitrarily, right? So let's say we root the tree here. And I'm going to draw a larger tree for sake of example. And let's say we start here. And I'm going to run a DFS, so depth first search, down from this root node. And let's say I reach here first. Okay, so what I do is for this node, I basically compare with the target. I compare the amount it has to the target. So if the amount that this node has, if it's less than the target, then it needs to, the target amount of hay bales, then it needs to gain more, right? So it needs to gain more. So it needs to be this way. And if it's greater than the target, then it has extra that it can give. So it'll be pointing this way. And then, so we process that way, and then we return from the DFS, we process these. And then after processing this one, right? Let's say this one, for sake of example, is giving stuff to here. So then when we come back up to here, this node is going to have an extra, like plus whatever came from this. So instead of thinking of it as the original input value of like HI or whatever, we'll think of it as HI plus like the extra amount that was given from its children. And similarly, if this node was going, if the arrow was pointing the other way, if this node required more, then instead of thinking of it as having HI, we would think of it as having like HI minus. So we would think minus like some amount. So we would think of it as having like a deficit. And it could be a negative value temporarily, but it will be fixed once we perform the operations in the correct order at the end. So we're just looking at pure values right now and like how much we should be moving from one to the other. So essentially at each node in the DFS, we're going to be deciding a direction of either like it gives to its parents, or the parents gives it, or do nothing at all if it already has exactly the right amount of value. And then we'll process them. Now for actually reconstructing the sequence, here's the idea. Let's say we're currently at this leaf node in the DFS, and this node requires, this node is going to give extra. Then if it's going to give extra, then this, it's clearly, then this node already has more than a target. So it's going to have enough to give. So we just perform this operation now. So what we do is we add this operation. We add this operation to the front of our sequence. So we do it first. And then on the other hand, if currently in our DFS, we're at this node and it requires more, we're going to, we want to first perform the operations relating to this vertex, and if this vertex receives more. So if it's so this is for if it's give, and on the other hand, if it takes, then we're simply gonna add this operation to the back, to the end. So perhaps I should give a more so going back to, I guess, here, this example. Here, let me go back to this example real quick. Yeah. So an example is if we're on, yeah. An example is that if we are on this leaf node, let's say we're considering this leaf node first. Ooh. Yeah, let's say we're considering this leaf node first. Then this gives, so what we're going to do is we're going to add an operation that says 5 to 3. So this is the output format, but the problem is that it's where it's from, where it's going to, and the amount. So we're going to go from the 5 node to the 3 node. I guess this is a little bit weird because I didn't label these nodes. So yeah, let me label these nodes. So 1, 2, 3, 4, 5, 6, 7. Yeah, so the labels here would not be 5 and 3. They would be 4 and 5. So from 4 to 5, I'm going to give 1. And that's going to be at the end of the sequence. Similarly, for this one, this is a take. So I'm also going to put this at the end of my sequence. 4 gives node 6, 3. And this one is also going to be at the end of the sequence. So I'm going to put it at the end. And I guess when I say end, I mean like it's going to be when I say end, I guess I don't really mean like end as like here. I mean end is like one of them's going to be building from the back and one is going to be building from the front. So for two things that I put like both at the front, they're going to be in the order that I put them in. And similarly, for two things that I put in the back, they're going to be in the order going backwards of where I put it from. So if I go like for this next one, this one here is also a take. So it's going to be 4 needs to give 7, 2. Okay, now I'm on this one. So as I said before, it gives 5. So 3 is going to need to give 4 a total of 5. Now let's talk about, okay, let's talk about this one because this is an example of a give. So this one is like the vertex has too many and it's giving extra. So I'm going to shift this over a little bit. And so here, this one is like, this one is that this node has extra and it's giving it to this adjacent vertex. So here it would be 1 gives 3, a total of 3, and that's going to be at the front, as I said before. And similarly, this one is also going to be at near the built from the front. So it's going to be 2 gives 3, a total of 4. And so my entire sequence will be this way. So it'll be first this one, then this one, and then after, so first 1 gives to 3 and 2 gives to 3. And after that, it will be like 3 gives to 4. They'll have enough. And then 4 gives to 7, 4 gives to 6, and 4 gives to 5, which is precisely the correct order that we want. And that's how we can reconstruct the sequence in at the same time that we're calculating the values and doing the DFS. So it ends up being quite slick to implement this. All right, let me see if I have any, questions. Yeah, any questions on this first problem? Yes. So the ordering is that so you understand how we put these arrows here, right? It's the arrows come from repeatedly taking leaves and figuring out, does this leaf require more or does it give to its parent? And then that's determines the direction of these blue arrows. And then we just need to construct a sequence so that these blue arrows are kind of like in order. So we don't ever like go from something later to something earlier. And so the way I'm constructing a sequence is if it's in my DFS, if it's a downward pointing arrow, if it's pointing to the leaf, then I have to wait. Then I have to wait to perform this operation. So I'm going to put it in the back. And if it's a arrow pointing from the leaf upwards, it's a leaf giving extra. So I can just do this operation now. So I'm going to put it in the front. And so I'm building the sequence both from the front and from the back. And then when I'm done, I'm going to have the total sequence in the correct order. Yeah. So for the actual implementation, this could look like it could look like two stacks, or it could look like you have a single array of size n-1. And then anytime you put in the front, you have a front pointer and a back pointer. And each time you put something in the front, you increment the pointer. Each time you put something in the back, you decrement the pointer. And then you delete the empty space in the middle at the end. Sorry. Yeah. Yeah, so I mean they're not pointing in the same direction. It's like when I DFS, like I guess you can think of it as from the perspective of up versus down if you're doing like the DFS. So when you DFS, right, each vertex is going to be each leaf is going to be either be pointing up or pointing down. Yeah, so and the premise is like the pointing up is like you're giving, so that goes in the front, and pointing down is your taking, so that goes in the back. So you want to do it, it's about you want to do it first versus you do it last. Right? Because like if you're pointing down, you want to put it near the last because you need to wait for your parents to receive the necessary stuff first. And if you're going up, if you're pointing out, you have enough, so you can just put it at the front instead. All right, any other questions? Yeah. Also, we'll come back. We can come back to. I mean, I can also answer more questions at the end as well. So, for now, because we do have two other problems to cover. I want to make sure we have enough time for them. I'm going to go ahead and proceed to the second problem. So I guess yeah, second problem is an interesting one. So in the second problem, we have a circular barn with a bunch of values, also of length n. And I should be writing bounds for these. So n is, in this problem, the previous problem was like 10 to the 5 as well. For this problem, n is also up to 10 to the 5. And you have a bunch of values written in this barn. So let's say you have a circle of, like, I don't know, 5, 7, 8, 2, 3, 1, 5, 4, something like that. So basically numbers surrounding a circle, and all the values are less than or equal to 5 times 10 to the 6. Yeah, and so we also have two farmers, Farmer John and Farmer the Hodge, and they are play a game where they start from the first barn, and they basically John makes a move and the Hodge makes a move, and John and I'll just say these are like the first and second players basically. So essentially, the first player A makes a move and player B makes a move, and then they move to the next one. Player A makes a move, player B makes a move. Next one, A and B makes a move, so on and so forth. They go around the circle, and then when they come back to here, A makes a move, B makes a move again. So basically, each time they visit one of the barns, each player makes one move, So John makes a move and Nahaj makes a move, and John always goes first. And what do we want to know? Well, first off, what does a move mean? What are we even doing here? So a move is that in one move you can subtract 1 or any prime number, provided that it is like less than or equal to AI. So you can't make a negative, but you can subtract 1 or any prime number. And if you can't make a move, then you lose. And the question is, if both players play optimally, so that means that both Farmer John and Farmer Nahaj have done all the calculations. They know exactly like what the optimal strategy is, as well as like what the optimal strategy for the other person is. Like they know everything basically. They've calculated it out, and they're going to perform these moves like exactly as planned. So given that situation, both players play optimally. Who wins the game? That's what we have to figure out. Yeah. So all right. So I guess how can we approach this? So I think the first thing we should consider is, I mean, there's no so within each of these barns, right? What the optimal move is for a given barn. So what value I should subtract from this 5, for example. This doesn't really have, or maybe it helps to start with like just starting from one barn, right? So like if it's just a single value of 5, let's say if it's just a single value, then who wins? Now 5 is kind of a simple example because 5 is prime. So in the first move, Farmer John can just immediately subtract 5 and make it 0. So in move 1, you subtract 5 and you make it 0. And then in move 2, Farmer Nahaj can't do anything, so they lose. So in this case, if we are looking at 5, then Farmer John would win. So let's figure out in general who wins for all sets of values. So let's make a table here. We have value. And then we have, I guess I'll say who wins, or actually, I'm gonna do it this way. I'm gonna say whether it's a win or loss, or a winning or losing state. And so what I mean by that is basically if someone were to walk up and it's their turn and they see the number 4, do they have a winning strategy or a losing strategy? And then finally, I'm going to figure out how many moves it takes, the number of moves. And this is important because this is going to be important for going back to the circle later. But for now, we're just doing with single values. So I'm going to write 1, 2, 3, 4. So I'm going to write out the first few values. I'll go up to 10, and we can quickly fill out this table. So, okay, so let's start with value 1. This is a winning state because if you see a 1, then your move could just be to subtract 1, and then it becomes 0. And that happens in one move. And actually, I'm going to say 2 moves because it also takes 1 move to lose. So this includes losing. Yeah. So what I mean by that is that if I reduce it to 0, but then the other person doesn't make a move, then you have to, if I make a move and I reduce the value to 0, but then like we move to something else on the circle, we have to wait until we all come all the way back to that value again on the circle before the next player would lose. So that's why I'm also counting losing as a move. Okay, so 2, by similar logic, 2 is also a winning state because I can just subtract 2. 2 is prime, and that's it. So it's 2. 3 is also a winning state, and 5 is also a winning state by the same logic. And so are 7. 4 is our first non-trivial case. So what happens in 4? If I see 4, I have a few options, right? 4, I can subtract 1 to go to 3, but we know that 3 is a winning state. Like if it's 3's turn, they would just subtract 3 and make it 0. So I don't want to do that. My other option, I can also subtract 2, but we also know that 2 is a winning state, right? Because the opponent can just subtract 2 and reduce to 0. I also don't want to do that. And from here, I can also subtract 3, but again, 1 is a winning state, my opponent will just subtract 1 and reduce to 0. So if I'm at 4, no matter what move I make, my opponent has a way to force themselves to win. So specifically, like no matter what move I make, my opponent's going to be left with a prime number or 1. So this is a losing state. And the number of moves it would take is 3, right? Because no matter what move I make, it'll reduce to either like 3, 2, or 1, and all 3 of them take 2 moves. Okay, let's look at 6 now. So is 6 a winning or losing state? Interesting enough, 6 is actually a winning state because I can simply subtract 2, which is a prime number, and get to 4. And I know from my table that 4 is a losing state. So therefore, if I subtract 2, then I win. And doing that takes 4 moves. Now, I want to talk about the moves for a second because you'll probably notice that like there are multiple ways you could win a game. And depending on what like way you choose, you might use a different number of moves. So how should we calculate this moves column? And I guess the short answer is that if it's a winning state, then I want to win as fast as possible, right? Because the faster I win, the more likely it is that like the less times I have to go around the circle before I come back to this state and before I come back to this barn and end up being the winner. So I want to go win as fast as possible. And if it's a losing state, then I want to stall. I want to make it as slow as possible. And that's because if I already know that that the game at this particular barn is like doomed, if I can't win, then I want to stall so that maybe in one of the other barns that we're going to visit when going around the circle, I win there first before I lose here, because we're going around the circle in the real problem. So yeah, so that's the strategy here. That's how we're calculating these numbers. So 4 is as fast as possible because 2 is the only 4 is the only losing state, and 4 takes 3 moves. Okay, let's talk about 8 now. 8 is actually a losing state, and you can try it for yourself, all the possibilities. You will find that there is no way for 8 to transition to another losing state. And so the optimal strategy for 8 is to subtract 2 and go to 6 and take 5 moves, because remember that when we're losing, we want to stall. So our best move is to subtract 2 and go to 6, which has the most number of moves taken. Similarly, I'll say right now 10 is also a winning state because we can just subtract 2 and go to 8 for 6 moves, and we have no other options. 9 is a bit of an interesting one. So 9 is going to be actually a winning state, and that is because we can choose to transition to, actually there are 2 ways for 9 to win. I can subtract 1 and transition to 8, or I can subtract 5 and I can go to 4. Now, it is more, since I'm trying to win as fast as possible, I should subtract 5 to transition to the 4 state, and that will take 4 moves. This is the optimal transition. Now I'm going to fill out just a few more values so we can observe the pattern here, because observing patterns is a good way to solve problems. So I'll go up to 16, and we'll quickly find here that 11 is a winning state because it's prime. And when it's a prime number, then to win as fast as possible, we just subtract the number itself, right? So 11 is prime. 12 is going to be a losing state, and 16 is also a losing state. And I didn't know that before I even filled in, and maybe you already, and hope you all might see the pattern as well. 14 is also a winning state, and its option is to subtract 2 and go to 12, which is a losing state. 13 is a winning state, it's prime, and 15 is a winning state. And one method is that we can subtract, let's see, our options are we can subtract 3 to go to 12, we can subtract 7 to go to 8, and we can subtract 11 to go to 4. And so we're going to subtract 11 to go to 4. That's the best option, and we take 3 plus 1 or 4 moves. All right, so by now you might be observing a pattern, and it's not hard to prove, but the hunch tells us that it looks like for every 4, it looks like the multiples of 4s are losing and everything else is winning. So 0 mod 4 is a losing, and everything else is winning. And this kind of intuitively makes sense because when you're at a multiple of 4, well, first off, I guess it kind of makes sense to think about like recursively how we're building this. At any point, the odd numbers are always winning states. So if you're at a multiple of 4, then if you transition to an odd number, that's going to be a winning state for the opponent. You don't want to do that. So you want to transition to another losing state. But because the losing states previously are all multiples of 4, you have to like subtract 4 or subtract 8 or subtract some multiple of 4 in order to reach a losing state, which is not possible because multiples of 4 are not prime. And so every multiple of 4 kind of like inductively gets proved to be a losing state. And on the other hand, for odd numbers, if it's prime, then, well, let's first talk about even numbers that are not divisible by 4. So like 6, 10, and 14. Why are these winning states? Well, from 6, 10, or 14, we can always subtract 2 to transition to a multiple of 4. So these are winning states. And similarly, if you're in a multiple of 4, that's also why if you're in a multiple of 4, you can't subtract 2 because subtracting 2 will get you to a non-multiple of 4 that happens to be a winning state. So yeah, multiples of 2, even numbers that are not divisible by 4, so 2 mod 4 are winning states. And then finally, for odd numbers, like 9, for example, odd numbers are not prime. So 9 is a winning state. And the easiest way to show that is that you can always choose one of -3 or -1 or -3. And one of these two is guaranteed to land on 0 mod 4, which we already showed was a losing state. So 9 and like 15 and all these other like odd numbers that are not prime are also winning states. Now I guess it's not to formally prove this, you would have to do like some sort of proof by induction, because if you just kind of skip around and consider different cases, then you're not really like you're kind of assuming the conclusion of one case to prove the other case. So to formally prove this, you would have to make an inductive argument where you start from n equals 1, n equals 2, and you build your way up. But you can prove it for all the cases. Okay, and then the other part is we can talk about the number of moves, because once we determine the number of moves that each game takes, then we kind of solve the original problem. Because in the original problem, we just need to figure out which thing runs out first, and that's just which thing runs out first. Specifically, because we take two moves per like visit in the circle, whichever one has the smallest like ceiling of moves divided by 2, this is going to be runs out first. This is going to be the one that runs out first. And so this is going to be the decider for our game. So all that remains is to calculate the number of moves it takes for each value from 1 to 5 times 10 to the 6. Okay, so before I proceed, let me make sure, are there any questions on anything covered so far? So kind of like the motivation behind like we're considering like whether these numbers are winning or losing states. We're doing some analysis and we found these conclusions that 0 mod 4 is losing and everything else is winning. And now we just need to figure out the number of moves that it takes. All right, so let's finish this problem now. So the final part is to figure out the move count. So as I said, so let's take a look at this table here. And actually, we already started deducing some stuff. So if it's prime, then obviously the answer is 2, right? You just subtract the number itself, and then your opponent loses on the next move. If it's non-prime, then if it's even, then you can very clearly see from the table that it's like a divided by 2 plus 1. And actually, the way you prove that is like initially the answer for 2 is 2. And then each subsequent even number, you subtract 2 to get to the previous. Because for the losing state, you want to delay it as long as possible. So you subtract 2 to get to the previous, which we're proving to be take the most amount of time. And then for the odd, or for the 2 mod 4 states, like 6, 10, 14, their only option, the only like losing state they can transition to is to subtract 2. Because like the losing states are on 0 mod 4, so you can either subtract 2 or 6 or 10, but 2 is the only prime number out of those options. So yeah, even is just a over 2 plus 1. The last case is odd and not prime. So these are, and unfortunately for odd not prime, there was no like easy formula that we just plug in, but we can kind of compute it because let's think about, for example, let's say we're computing the answer for 99. 99 is not prime, but it's odd. Then remember that the losing states are multiples of 4. So 99 is going to either need to go to 4 or 8 or 12 or 16, one of these options. And so each of these differences are going to be, let's see, 95 is not prime. 91 is, I believe, not prime. 87, I think 87 is not prime. Divisible by 3. 83. I mean, I won't go into the details, but the point, you kind of get the point, right? The idea is that you want to find you basically want to find the largest prime digit, the largest prime step, such that 99, largest prime p, such that 99 mod minus p is equal to a multiple of 4, so it's 0 mod 4. And this can be computed this can be like done formulated as a computation problem. So as we're computing the states, so if we're doing a for loop for like we're computing all the answers from 1 to 5 times 10 to the 6. Then while we're doing that, we can just maintain for 0 mod 4, or we can just maintain for 1 mod 4 and 3 mod 4, because notice that another way of saying that 99 minus p is equal to 0 mod 4 is saying that 99 mod 4 is equal to our prime number mod 4. So if we just keep track of, while we're computing the values, the largest prime number so far for each of 1 mod 4 or 3 mod 4, then we're done. Because then when it's time to compute something like 99 is congruent to 3 mod 4. So we just look in our computation and see what is the largest prime number so far that we've encountered that is congruent to 3 mod 4. And by the way, the reason I only write 1 and 3 here is because I don't need to consider 0 mod 4 or 2 mod 4, because those are even numbers and I'm only worried about odd numbers. Yeah, so the final, so to put it all together, there's a so first, before we deal with the barn, we pre-compute the answer for 1 to 5 times 10 to the 6. So we pre-compute whether it's a winning or a losing state, which is simply based on whether it's 0 mod 4 or not. And for the moves, we just use the rule of if it's a prime number, it's 2. If it's even, it's a over 2 plus 1. And if it's odd, then we do this procedure of like kind of computing the largest prime number in the same modulo class as it. And then for actually computing the prime numbers, I won't get into too much details, but there's a fairly standard technique called like prime or sieve of Eratosthenes. I'm not gonna try to spell his name, but you can look it up. This is a method that computes all the prime numbers from n, all the prime numbers less than or equal to n in n log n. So you said almost linear time, but definitely fast enough for 5 times 10 to the 6. And that's how you actually compute like which numbers are prime. All right, so that's and then once you compute all of this, once you compute the answer, you simply find in the circle the first the barn with the smallest ceiling of moves over 2 counts, because each time you visit the barn, you perform 2 moves. Farmer John makes a move and Farmer the Hodge makes a move. And the smallest one is going to be the one that gets stuck at first, and that's going to determine who wins. And for tiebreaker, it'll be the earliest. All right. And that concludes the second problem. So let me see if anyone has any questions. Yeah, the number of moves is solely dependent on the number. Yeah, it has nothing to do with the circle, really. It's like you just pre-compute for each number how many moves it's going to take, and then whichever number requires the least number of moves, that's like the bottleneck. That's like where you get stuck first. Or not just least number of moves, it's like ceiling of moves over 2. Because a number that takes like 2 moves, a number that takes 3 moves, and a number that takes 4 moves are going to both get visited in the same round around in the same like bout around the circle. So even if the 4 moves come before the 3, this one will be the bottleneck first, because the first time around you'll do 2 moves on both of them, and the second time around you will get stuck on this one first. So that's why it's ceiling of moves over 2. This is the number of moves for assigned to that particular number. So in that table we talked about earlier. Oh yeah. So we did talk. Yeah. So yeah, I guess if we want to talk about if we want to talk about whether this is optimal, I guess we kind of So I guess improving why these are winning or losing states, we kind of alluded to why it's optimal, because like, well, prime number 2 is obviously optimal. You can't do like you literally cannot do better than 2. That's not thought physically possible. For your even, a over 2 plus 1 is optimal, because if you are a losing state, you want to delay for as long as you can. So you subtract 2 to get to the previous even number, which we're also proving to be the longest possible. And then if you're at an even number that's not a multiple of 4, your only valid transition to get to a losing state is to subtract 2 to get to a multiple of 4. So a over 2 plus 1 is also the guarantee to be the number of moves for even numbers. And for odd numbers, the reason we're using the largest prime is because, like, the reason we're using the largest prime is because the larger the prime, the larger the jump, and the smaller the state we transition to, and smaller multiples of 4 take less moves. So it's optimal to jump with the largest prime number possible. Yeah, so it's all about a minimized number of moves or maximized number of moves, depending on whether it's a winning or losing state. That's how these are calculated. All right, I'm gonna move on to the third problem now for the sake of time. I guess last thing. I mean, multiples of 4 is like, I'm not sure what you mean by calculates. It's just like you check if it's a multiple of 4 or not. Yeah. Yeah, number of steps. Yeah, multiple of 4 is in here, right? It's even. So it's a over 2 plus 1. Yeah. Yeah. All right. So for the sake of time, let me go to the last problem now. So our final problem. So our final problem is a constructive. So they basically give us, let's say you have some array A1, A2, up to AN. Then what happens is R of IJ is defined as, so they give you a 2D table, R, and an entry Rij is equal to the maximum of all values between I and j inclusive. So maximum of AI plus 1, up to AJ, minus the minimum of AI plus 1, up to AJ. And so now the problem is they give you R, and you want to reconstruct A. That's the entire problem. Okay, so how can we approach this problem? Some observations. The first observation is, if we can, let's consider like adjacent entries, like for example, A1, in A1, A2, dot up to AN. If we consider just like R1, 2, that is just equal to the maximum in this between A1 and A2 minus the minimum between A1 and A2. So in other words, it's just equal to the difference between the two values. It's equal to the absolute value of the difference of A2 minus A1. I say absolute value because it's possible for A1 to be greater than A2, in which case it will be the other way around, right? And similarly, R2, 3 is equal to just absolute value of A3 minus A2, and so on. So in general, R of I, comma, I plus 1 is equal to the absolute difference of between AI plus 1 and AI. So right off the bat, if we just look at these entries, we already have the difference array up to like a plus or minus. So our real task is just like to figure out for these difference arrays, should they go up, should it be positive, or should they go down, negative? That's really our only task for reconstructing the array. Yeah. So, okay. Next, I guess we can always make A1 equal to 0, just because like, why not? Like, this entire table is only based on differences. So we can always like shift the entire array up or down by a constant, and it's still going to be the same, have the same like R table. So might as well make the first value 0. And A2 can either equal R12 or negative R12, right? Because we can either go up or we can go down. And so I'll say without loss generality, we can always make A2 equal R12 because we can always make the first one go up. Because if we make it go down, if there's a solution that if there's a solution that works and the first one goes down, we can just negate every single value and it will be going up instead, and it will have the same like R table. Okay, now we're basically just going to reconstruct the array element by element. So let's say we've reconstructed A1, A2, up to AI, and now we want to know like what does AI plus 1 equal? Well, R of I plus 1 is going to give us the difference between AI and AI plus 1. And we want to know, should we add the difference or should we subtract the difference? And so here's a nice way of looking at it. So let's say AI plus 1, we have two candidates. We can either go up or down. And we have a previous value. Let's say AI minus 1 is less than AI, because if it's greater than, it's a similar process. Now here's the neat thing. If AI plus 1 goes up, if AI plus 1 should go up, then what if we look at R of I minus 1, I plus 1? So intuitively, the reason we're looking at this is because like we're trying to like keep things simple. Because like if we have like only two, we're only looking at like two or subrace size 2 or subrace size 3, we only have to worry. It's very easy to know what the minimum and maximum are. In this case, if AI plus 1 were to go up, then the maximum will be AI plus 1, the minimum will be AI minus 1. And so the difference will be precisely equal to R of I minus 1, I, plus R of I I plus 1. On the other hand, if that was not the case, if the true value of AI plus 1 goes down, then clearly then the maximum is going to be AI. The minimum is going to be either AI minus 1 or AI plus 1. But the point is that R of I minus 1, I plus 1 would not be equal to Ri minus 1 I plus Ri I plus 1 in this case. And so we can actually just figure it out right here, like whether we should go up or down. We simply look at the previous element, the previous two elements, and we say, okay, if Ri minus 1 to I plus I to I plus 1 equals I minus 1 to I plus 1, then we go up, otherwise go down. And that's how we determine AI plus 1. Now we're technically not done yet. I left out one tiny detail. It's not the detail is that let's say it was 5 and 5, and now we're determining what value should this be. The issue is that the difference here is 0. And unfortunately, 0 doesn't tell us anything about whether we should go up or down, because in both cases, the sum of the difference, in both cases, this difference is still going to be like the same. Like R of I minus 1, I plus 1 is still going to be correct in both cases. And so the solution is just look at the one before that. If it's 3, then just base it on this instead. Base it on this difference instead. See if this difference plus this equals this. And similarly, if the previous was also 5, then just go back one more step. So basically just like skip over the zeros and look at the previous one. And if no such value exists, if this is at the very beginning, if it's at the very beginning, like 0 to 0 to 0 to 0 to 0, and this is our first non-trivial decision, then we can just always go up, because remember, without loss generality, the first choice we make can always be positive, right? I said here, the first choice can always be going up. So that's the full solution. The full solution is to carefully account for the zeros. We just look at the first like non-zero difference and base it off of that. And if there is no previous non-zero difference, then we can choose arbitrarily. It doesn't matter. And that lets us reconstruct the entire array. And so if implementation be, I guess technically this is only O of n, but because like reading inputs already takes like n squared. So that's kind of the bottleneck. But either way, for this problem, n is only less than 300, so this is sufficient to pass. All right, so any questions on this problem? Oh, yeah. So, I mean, if you do it naively, like you just do a for loop backwards to find the previous non-zeros n squared, but you can also do a kind of like a two-pointer type thing to make it linear time. It's not required for the problem since n is loose bounds, but yes. Yeah, so this is O of n if you use like some sort of two pointers to skip zeros. Yeah. Yeah, so ultimately, yeah, the ranges we're checking is pretty much just the adjacent, the smallest ones possible. So it's like to make the next decision, we're looking at the adjacent range of Ri, I plus 1. And then if the previous one was here, then we use this range plus this range. We want to see if it equals this range. And if it does, then we know it goes in the same direction. Yeah, so similarly, I guess if it was previously going down, and then whether it goes down again is whether like this one plus this one equals the whole thing. So as I said before, if it went down previously, then it's all about like same direction versus different direction. All right, any other questions? That's a good question. Yeah, how do you know that it satisfies all of the ranges? So that's a good point. So this is a very important, yeah, actually, I should have mentioned this earlier, but yeah, the statement does say is guaranteed there exists a solution. So we don't have to worry about conflicting entries. We don't have to worry about conflicting entries in our R table that they give us. So here's so I guess the point here is that like there is only one valid decision to make for aside from the very beginning, there was only one valid decision to make of up versus down. So if the only valid decision we make doesn't work, then that means there's a conflict in the R table, which would conflict this guarantee. So it's more about like we're deciding like should we go up or down at this point, and we realize that like there's only one choice we can make, up or down, and that's can be determined by looking at previous terms. And I guess the guarantee, I guess the one choice we make is up to like a difference, right? So for example, the first term I said was 0 because if I make that term anything else, like 1 or 2, I mean that's just a constant shift of all the values, which doesn't affect the R table. Yeah. Yeah, so yeah. So yeah, someone said we're only using RI I plus 1 and RI I plus 2. Yeah, exactly. Well, I guess except for the special case where you have to skip over the zeros, but so you'll be using the one before the zeros, the one after the zeros, and the total. Yeah. Yeah, actually, yeah. It's nice to point it out. The problem says that all the values we print have to be between 10 to the 9 and between 10 to the 9, like all the values we print. But the inputs, the R values, are also less than equal to 10 to the 9. And actually, you can try to think about it yourself. Why is this true? But if we use our procedure here, it is guaranteed that the array we construct is also between 10 to the 9, negative and positive, if we use this procedure. So we don't even have to worry about this. This kind of just happens automatically. And I'll leave you to think about why that is the case. Yeah. How much time do we have left? Just want to make sure we have enough time for. Yeah, I can always talk a little bit. I guess like I did see some people ask some like kind of like meta questions about like just like approach to USACO, thoughts about the contest, etc. I guess for this, yeah, I guess first off, my opinion on difficulty of these problems, I think it's like P1 less than P. I think it's problem 1 is less than 3 is less than 2. I would say 2 is the. Or I mean, I think these are debatable because 2, I think 3, I think 3 is kind of just like you need to approach it in the right, I guess, in the right way. Whereas 2 has kind of like a more systematic way of approaching it. With 2, even if you're stuck, you can still like you just like sit there and like make a table at the very least, and then like try to find a pattern from this. Whereas 3, like if you don't have an idea of like how to start building the sequence, it's hard to like pluck it out of nowhere. So I think this is like kind of depends on. I think this will kind of depend on like what you feel is like, yeah. Yeah, so I guess some general thoughts also on the contest and building intuition. Yeah, way you gain intuition is kind of like through like practice and doing problems. And actually, we will talk about it later because I'm going to be talking about like some of the opportunities XCamp has for taking for classes and how we help you prepare for doing these types of problems. So actually, I figure we might as well transition from there then. Yeah.
Thank you, Max.
Yeah.
Yeah, I think there's still a lot of questions in the chat.
Yeah.
See that. We have several slides. How about you help us to go through that? And definitely students can keep here and asking. We still have maybe some time if you are available, Max. Right?
Mm-hmm.
Okay.
Yeah.
Share my screen now. You have a couple slides. You can go continue. Go over with that. Do you see my slides?
Yeah, I can see it. Yeah. All right. So classes. Yes. XCamp, we offer a lot of classes. I think I won't read like the entire slide, but kind of the general gist is like, and I think like I'll talk a little more about like, why I think like where I think like XCamp is unique in this aspect is like, aside from just like the quality of coaching and stuff, I think we put a lot of emphasis to not just teaching you concepts or not just teaching you like algorithms and concepts, which is I think a lot of other people do, but we actually like train students. Like we design homeworks and like training regimens and like mock tests. We design them with the intent of like helping students like improve and and we provide the environment for them to like work with other students and discuss problems together and really just like think and not just like not just like receive information. Because I think that's what really sets apart like just like reading a book or just like reading a book or just studying on your own. It's like you don't really get the environments of like of other students to like compete with and like think about stuff with, and you also don't get like the specific like the specific like training regimen that like all the teachers like kind of provide their students, because like the teachers specifically like, choose problems that they feel are relevant to preparing for the contests. Put a lot of time to doing that. The mock tests are specifically designed to like simulate like a real contest. They specifically are to include these like types of tricky problems that we saw in today's USACO contest, and not just like standard application of binary search or BFS. So I think that's really like the main advantage of signing up for one of these classes, just getting like kind of more focused and curated like training plan versus just like doing things randomly on your own and hoping it works out. Yeah. Yes. So yeah, we do have we have a couple opportunities coming up to prepare for USACO. I think the most we have a mock test. Our most our upcoming or most recent like upcoming thing is like the winter camp. We got gold and platinum camp still has openings left. I guess silver not at the moment, but it's we have opportunities. Yeah, we also have our weekly classes. This is for building up knowledge, but also just kind of like getting like and knowledge is not just like algorithms, but it's like common tricks for these problems, ways to approach problems, just like creative thinking, and just like getting that as I said before, getting that like curated problem list and the training and the different training resources. Yeah. Yeah. So yeah, I will leave the remaining time to answer questions. I know there's a bunch of questions that I still haven't gotten to yet, and I do want to make sure to cover all of them. Yeah. So yeah, you can absolutely. So if you have any questions about either the problems or just about like USACO as a whole, I'll be willing to answer them.
Yeah. Any other questions, students?
Yeah, I think people were asking earlier, just talking about like thoughts on the contest, and yeah, I would say this contest is it's certainly a little different than like I think previous contests. I think there were like almost no algorithms used here, but I think this is also a little bit expected. Or I think USACO was always kind of trying to move in that direction. They're trying to move away from just like these book or template questions that you can just study from a textbook, and like trying to move to like forcing you to think about these problems, and or it's kind of like putting more emphasis on having experience and good intuition. Yeah, and for building intuition, I think it's just like aside from practicing, I guess like the general thought process, how to approach problem thinking. I think a lot of times it's like you look at a problem and you think about like for example, I think each of the problems I mentioned today, I had like I have a specific like way of like like thinking about how to approach this problem. Like for the first problem, it was about trees. It's hard to like start from the middle, so I like to think about starting from leaves will often get you somewhere, and in this case, it did get us somewhere. It gave us a procedure for reconstructing the answer. For the second problem, it was not immediately obvious like how to approach it at like if I just stared at the problem statement, I wouldn't be able to guess that like, oh, 0 mod 4 is a winning state. But by writing out the table and doing something, we were able to observe that pattern and get to that conclusion. And then problem 3 is like, I think problem 3 is just like the way you think about a solution like that is you think like you want to start small, right? It's hard to like just use the entire table like R from 1 to n to like do something productive. So if we look at like adjacent terms, which is the smallest we can possibly get, maybe we can reconstruct something from there. Yeah, what do I think cutoff? Yeah, 700 is a fair cutoff. Maybe even 750 because like I've heard some other people like say it's a easier contest than usual, but it all depends on who you ask. Yeah, I think generally historically it's always between like 650 or 800. I think like if it's anything outside of that, then it's the extreme case. I don't think this is an extreme case. I think it's yeah, I think 750 or 700 is maybe a safe bet. Yeah. I'd be a little surprised if it's 800.
Yeah, thank you, Max. We're kind of out of time. Also,
Yeah.
thank you all the students to attend this session. Yeah, congratulations for those who most likely pass this contest. But for those that might be short, just keep up. Contest is just a way to, to test what you learn. Just keep up learning. That's the most important thing. Okay, thank you again, Max. Thank you all, and have a nice weekend and happy holidays. Bye.